Good morning to everyone. I welcome you all here for my course, Engineering Thermodynamics. Today I am in my topic, Introduction to Thermodynamic Properties. In this, first I will go for the introduction of the thermodynamics and what is the meaning of thermodynamics. The name thermodynamics stems from the Greek word thermi, that is heat, and dynamics means power. So thermodynamics means the power which is generated by the help of heat. So it is very conventional definition of the thermodynamics, which is most descriptive of the early effort to convert heat into the power. So if you see the olden days engine, they were made of the steam engine, and this steam engine were first heated, the water was heated, and this heated vapors were used to operate the engine. So which was the very early efforts in 18th century we used to do like this. So from that time this definition has started. Today it is included all aspects of energy and energy transformation, including power generation, refrigeration, and relationship among the properties of matter. So in olden days it was heat to power, how we can convert, and this was known as the heat thermodynamics. But as of now we are in the advanced stage, so it is not only the heat and the power. Today we all include that aspect of energy and energy transformation, including power generation, refrigeration, and relationship among the properties of the matter. So here these properties of the matter, a very important aspect of thermodynamics, and I am dealing today few properties related to the matter on this class. We should know about the conservation of energy principle. And what is that? It states that during an interaction, energy can change from one form to another, but the total amount of energy remains constant. So that is the statement of the conservation of energy, that during the interaction energy can change from one form to another, but the total amount of energy remains constant. That is, energy cannot be created and nor destroyed. So here I am showing one how energy conversion can take place. So this you can see here, that a rock falling off a cliff. So if you see here in this rock we have the potential energy, it is 10 units, and here it is stable and it is kept here, and here the kinetic energy is 0. So here only we have the potential energy, but if you drop from here, this potential energy which was 10, after some height the potential energy is now 7 units and kinetic energy is 10. So still here we have the 10 units of energy. And if you reach at here in this point at the ground, here you will have PE is equal to 0 and KE is equal to 10. So at each point you are having the same amount of energy, and this is called the conservation of energy and the conservation of principle of energy. So this energy is very much useful, and this is also known as the first law of thermodynamics, that I will be discussing next slide, and further I will take only one lecture only for the first law of thermodynamics, then second law of thermodynamics. This I will be discussing in due course of time. Now I will take the second example. First I have taken that rock falling from the cliff. So now the second example, if you see, the conservation of energy principle also forms the backbone of the diet industry. You know, some people are very fat, some people are very thin. So how your diet will be controlled? So there also how much you are intake and how much you are output. If there is imbalance or the input is more than the output, then you will get fat. So in direct industry, it is nowadays very much useful. This you can see here, the diagram here. Here one sumo is here, and this person energy is eating the 5 units. You can see the 5 chapatis he is eating, and the work which is obtained by this person is only 4 unit. Means it is walking, running, or anything, he is doing some wrestling and all. So he is using only 4 units. So the remaining 1 unit energy storage, this you can see here, this energy storage in his body here, and he is getting fat. Much fat, he will be becoming the much fatter. So like this, it is also simple example for the energy balance. So here conservation of energy principle for the human body. So this is the human body. For this human body, the conservation of energy can be applied. Now just same way we have the first law of thermodynamics. So in this basic, it is a conservation of energy. The first law of thermodynamics is simply an expression of the conservation of energy principle and asserts that energy is a thermodynamic property and it is conserved. So energy is also a thermodynamic property and a specific internal energy, which is a thermodynamic property, and this is emphasizing that by the help of the first law of thermodynamics. The second law of thermodynamics states that it asserts that energy has quality as well as quantity, and actual process occur in the direction of decreasing quality of energy. So what happened in the second law, that energy will always flow from high energy level to low energy level. So this is the second law. It will never go from low to high if you don't add something. So that is a basic concept of the second law. I will be discussing so many classes about this first law and the thermodynamics, but today just I am giving a name, and in this you can have a little this thing that the energy has the quality and the quantity and actual process in the direction of the decreasing quality. So if high temperature to low temperature, high heat to low heat, like this it will work. Next, another example I am showing here, that a cup of hot coffee left on a table eventually cools, but a cup of cool coffee in the same room never gets hot by itself. So this is the principle of second law. The high temperature energy of the coffee is, once it is transferred to the surrounding air, this you can see here that how these things are happening. So here we have, so what is, this is the example for the second law of thermodynamics. It gives thermodynamics. So what is this? If you have a hot coffee of 70 degrees centigrade, inside you have the hot coffee here, it is filled with this, and slowly your heat will go out, and this 70 may become 30 degrees centigrade. So this high energy is mixed in the cool environment here, 20 degrees centigrade. This high temperature energy of the coffee is, once it is transferred to the surrounding air, it will never come back again. Okay, so it will, you cannot make your coffee again same temperature. That is the second law of thermodynamics. It states that if heat is transferred from the system to the surrounding, and this surrounding will not come back to the system. So you cannot make hot. Once it is cooled, it is not possible by the means, only you have to make some another arrangement to heat it. So heat flow in the direction of decreasing temperature. So here we have the 20, here we have the 70. So this will flow from this direction to this direction. Another way we can see here that if we can take a thermos bottle here, and it is very much insulated. This you can see, this is the insulation, and here we have the hot coffee. Here inside this we have the hot coffee, and this, because it is insulated, so heat will not go. Heat will not go in this direction. It will not go to the surrounding. It will remain there. So for long time, we can make coffee hot due to the thermos bottle. Okay, so this is the second law of thermodynamics, that if you make sure that your heat is not generated to the surrounding, the amount of heat will be same. The temperature will remain same. Now I will discuss about some properties of the system, and I will discuss first about the density and the specific gravity, because we know the state, to find the state of any thermodynamic conditions, we need to have some property. The basic properties of the thermodynamics, P, V and the T. But here if you see the density, and this is the pressure, this is the specific volume, and this is the temperature. But we need the density. But you know that this specific volume is equal to 1 by density. Normally till now we have studied about the density. We are not very much concentrated about the volume of this, the specific volume. But now in this thermodynamics, specific volume is a very important independent property, and this we should know, then only we can go ahead. So we should have the concept of the specific volume, specific gravity and all. In this way I am going to discuss about these properties. So here density is defined as mass per unit volume. So mass per unit volume. So here we can see that density is equal to, it is denoted as a rho. This rho is equal to mass m in kg, and V is in meter cube, where V is a volume and m is a mass. The reciprocal of the density is called the specific volume. So here I have shown just now. So reciprocal of the density is called the specific volume. So this V is equal to 1 by rho. Means specific volume is a inverse of or reciprocal of the density, where rho is a density, which is defined as the volume per unit mass. Volume per unit mass. So unit of this thing is meter cube per kg, and for the density it is a kg per meter cube. So this we have to understand very well. These things will be useful in future. So here specific volume, it is a small v is equal to capital V. It is a total volume divided by mass. So this is equal to 1 by rho. This, and we can see here that in this diagram that here it is shown that V is equal to 12 meter cube and mass is equal to 3 kg. So density is equal to what? Density is equal to, here if I put mass is equal to 3 and is equal to 12, this is 1 by 4, 0.25 kg per meter cube. But if you want to know specific volume, then volume by mass. So volume is 12 and mass is 3. You will get 4 meter cube per kg. So this is illustrated here. This we can find out the density or the specific volume here very well. There is no issue in that. So the reciprocal of the density is the specific volume V. which is defined as the volume per unit mass, and this specific volume is from small letter, and this is the total volume. So this specific volume is the property, not this. Total volume is not the property. So we can find out small v from the steam table, not the capital V. So if you know the V, we can find out the capital V is equal to mass into specific volume. So this we can convert it. So for a differential volume element of mass dm and the volume dV, the density can be expressed rho as a dm by dV. Change in mass, this we can write as a change in mass divided by change in volume. This is the expression for this. Now I will discuss the next topic is specific gravity. So what is the specific gravity? Sometimes the density of a substance is given relative to the density of well-known substance. Sometimes we have to relate with some other properties. So that time we need the specific gravity. So sometimes the density of a substance is given relative to the density of a well-known substance. Then it is called the specific gravity or relative density. And this relative density or specific gravity is defined as the ratio of the density of a substance to the density of some standard substance as a specified temperature. So suppose we want to compare which density is more with reference to the some standard substance like water or mercury or anything we have to take. So the specific gravity is defined as the ratio of the density of a substance to the density of some standard substance at a specified temperature. Usually water at 4 degrees centigrade, for which the density of the water is 1000 kg per meter cube. So a specific gravity we can write as a rho by rho H2O. So if you want to compare with the water, so a specific gravity will be rho is the density of that material or that substance divided by density of the water. So in this way we can compare. Here I have given the table, and this table shows some standard specific gravity. The specific gravity of some substances at 20 degrees centigrade and 1 atmosphere, means atmospheric condition, unless stated otherwise. The substance water specific gravity is 1, blood is 1.06, seawater is 1.026, gasoline is 0.68, ethyl alcohol is 0.790, mercury is 13.6, balsa wood is 0.17, dense oak wood is 0.93, gold is 19.3, bones 1.7 to 2.0, ice is 0.916. Just you can see the density of the ice is less than the density of the water. So ice will float on top of the water. So that you have to take very much care. And specific density of the air is 0.001204. So here we can see that the blood is heavier than the water, 6% heavier than the water, and seawater is 2.5% heavier than the normal water, and your petrol is 0.68, means 28% lighter than your water. Alcohol is some 11% lighter, and mercury is 13.6 times heavier. Balsa wood is very, very light than the water, so it can very much float. Other wood also, but balsa with the lightest wood and very strong. So this we can use in our aero modeling and other activities where we don't want much weight to be added. Now if you know the specific gravity, we should also know about specific weight The weight of a unit volume of a substance is called the specific weight or the weight density and is expressed as gamma S is equal to rho into Z, Newton per meter cube. So, weight of a unit mass of a substance is called the specific weight or weight density. So, this weight density gamma S is equal to rho G and the unit is Newton per meter cube. The densities of liquids are essentially constant and thus liquid can often be approximated as being the incompressible substances. Okay, so very important assumptions are here. Most of the liquids like water, alcohol and all, their densities are constant and thus liquid can often be approximated as being the incompressible substances. So this we can see here about this. So next I am going to discuss about state postulates. So what is the meaning of state postulate? So here the system is described by its properties and you know the properties are PVT and also there are some internal energy, enthalpy. These things are also properties. This property do not need to specify all the property in order to fix a state. So we don't, because we see that there P, V, T, S, then small u, these all are the property. But we don't need all the property to specify a particular state. If you know two properties for the pure substances or maximum three, we can find out all other state of the system. So we don't need more number of property. So do not need to specify all the property in order to fix a state. We need a maximum two properties to identify the state of any substance. Once a sufficient number of properties are specified, the rest of the property assumes certain values automatically. So once a sufficient number of properties are specified, the rest of the properties assumes certain value automatically. So if you know two properties, we can find out other because they all are related by some equations and accordingly we can find out by the help of the mathematical equations. Specifying a certain number of properties is sufficient to fix a state. So we need some amount, certain number of properties. So how many properties we required, that we can find out from the Gibbs equation. Okay, that I will be discussing in due course of time. The number of properties required to fix the state of a system is given by the state postulate. So what is the state postulate? The number of properties required to fix the state of a system is given by the state postulate. So this is called the state postulate. So state postulate is the number of properties required to fix the state of a given system. So that is called the state postulate. So by definition, we can say that the state of a simple compressible system, this I will be discussing in my next slide. What is the simple compressible system? The state of a simple compressible system is completely specified by two independent intensive properties. About these properties I have discussed in my previous classes. What is the independent property and intensive properties? So the state of a simple compressible systems, the simple compressible system means those who are following the gas equations, and also I will be full detail, I will go in my next slide. So the state of a simple compressible system is completely specified by two independent intensive properties. So what is the simple compressible system? A system is called a simple compressible system in the absence of electrical, magnetic, gravitational motion and surface tension effects. So a system is called a simple compressible system in the absence of electrical, magnetic, gravitational motion and surface tension. So if a system do not possess electrical, mechanical or gravitational or motion, then we can say that it is a simple compressible system. These effects are due to external force fields and are negligible for most engineers. So we see that for thermodynamic process, especially for the mechanical and other people, we are not concerned with electrical, magnetic and gravitational, all these forces. These effects are due to the external forces acting on this environment, and we can assume as a negligible for most of our work. So here the state postulate requires that two properties for simple compressible flow. For a simple compressible system, the state postulate requires that the two properties specified be independent to fix the state. So for any compressible system, we need two properties. So state postulate requires that two properties specified be independent to fix the state. So here you can see this diagram here. We have here one cylinder. This is the cylinder here, and this is the piston. And here inside we have the nitrogen. And to specify this state, we need two properties, either P, either V or RT. Any two properties, either this, either this, either this. Any two properties we can take. So here I have taken here T is equal to 25 degrees centigrade and V specific value is 0.9 meter cube per kg. If you know these two properties, remaining you can find out by the relations, thermodynamic relations, and or by using the tables, steam tables or air tables, nitrogen tables, ammonia tables, all type of tables are available. These all things you can find out directly. And so for any compressible substance, simple compressible substance, we need minimum two properties to specify its state. Two properties are independent, but these two properties should be independent, like PV, VT or PT. And if one property can be varied while the other one is held constant. So in this we can vary one and another we can make the constant. Temperature and specific volume, for example, here I have shown here temperature is equal to T. Temperature I have shown is equal to T, and specific volume I have seen V. It is given 25 degrees centigrade and this is given 0.9 meter cube per kg. So by this we can define the system and we can find out the state here, and this state is shown here. This you can see here, state 1. This is the state 1. And second state, if you see, if you increase the temperature, if you increase, initially it is a 25 degrees centigrade and this is the 0.9. If you increase the temperature, assume it is a 80 degrees centigrade. 80 degrees centigrade, and you got here somewhere 1.5 meter cube per kg. So like this, any two, in this process, a process is happening and you can find out the next stage. So in this way, we can find out the state points and we can solve our problems. So temperature and specific volume, for example, are always independent properties and together they can fix the state of a simple compressible system. So here the state of the nitrogen is fixed by two independent intensive properties, that is that T and the V. Here a process is shown here, a process between state 1 and the state 2, and the process path T and specific volume is shown here. So in this way the process you can, so here it is shown the property B and here is the property A. It can be PV or TV or PT, anything you can draw accordingly. But mostly we draw here in horizontal we draw the V, and vertical we can draw P and T. It is very convenient if we draw the specific volume on the x-axis or the horizontal axis, and because it is very easy to control the specific volume, you can increase or the decrease, and as per that we can find out. And on the vertical axis we have to put the variables which is to be measured after varying this x-axis parameters. So in this way we can put this diagram like this. Now I will discuss the steady flow process. So this you can see here, that what is the steady flow process. The term steady implies no change with time. So the steady means there is no change in the properties with the term steady implies no change with time, means time is fixed. At particular instant of time we are taking the values. The opposite of steady is unsteady or transient. So unsteady or the transient, if we take in a certain amount of time any values, then we can say that it is a unsteady or the transient. The term uniform, however, implies no change with location over a specified region. So no change the location over a specified region means it is a uniform, means in a whole area everywhere the temperatures are same or any properties which are same. A large number of engineering devices operates for long period of time under the same condition, called the steady flow devices. So just you can see here that so many equipments, turbines, compressor, AC, pumps, so many devices, your thermal power plant, all the things, they are working for a long time, continuous they are running, and they maintain the same condition. So we can assume that they are the steady flow devices. Such devices can be represented by idealized process called the steady flow process. So these systems, just now I have told, like a heat engine, IC engine, like piston engine, SI engine, CI engine, turbo engines, turbo shaft, turboprop engine, your thermal power plant, your air conditioner, these all devices, they are the steady flow processes. Such devices can be represented by an idealized process called the steady flow process. Defined as a process during which a fluid flow through a control volume is steadily. So steady flow process is what? For a given process during which fluid flow through a control volume is steadily. So just you can see here at time 1 here it is mass is going in 300, 255, 200 and 150 at 1 p.m. and after 2 hours also you see same temperature, same thing is maintained, but it is flow is going in and it is going out. Here also it is going and it is also going out, but inside this control volume, the red line, all the parameters will remain constant. That type of condition is called the steady flow process. So this is a very simple assumption that inside the control volume, all the temperature, pressure and everywhere in the particular location, it will remain constant. So that type of system is called the steady flow system, and this type of process is called the steady flow processes. During a steady flow process, fluid properties within the control volume may change with position, but not with time. Okay, so in this you can see that at 1 p.m. here 300, 252, but at 3 p.m. also they are maintaining the same location, same temperature it is maintaining. So it is a steady flow process. So like this we should understand, and these are the assumptions which we have to take for our solution of the problem on the thermodynamics. Now I will discuss about temperature and the zeroth law of thermodynamics. Actually this I have discussed, but I will go little here. So temperature as a measure of hotness or the coldness. So the temperature is, if you see this one, if I touch here and if I touch this table and this, and if I touch one metallic part, and if I touch the metal part in the same atmospheric, I will feel that the metal part is cooler than this plastic part. So how it can happen? If here I have here one pen, one is this. If I touch this one is different hotness and this much is different coolness. Oh, it means what? This is environment is different. Then how I am feeling that this is hot or this is the cold? Which one is hotter and which one is the cooler? But in the environment is the same temperature here. So it is not the environment, it is the transfer of energy. My body is having more energy than this environment. So my heat is transferring here faster in metal particle because metal parts, because the conduction of the metal is more than the conduction of the plastics. So in the plastic I don't feel much variation, but in the material or the metal like aluminum or copper or anything, I feel that the copper or aluminum is much colder than this plastic. But temperature of the environment is same. It is not due to this temperature, but it is heat transfer. My body is releasing heat because my body is much hotter than this, and the part of this material or metal is more conductive, more heat, much faster rate of heat transfer is taking place. So I feel that the copper piece is much colder than this plastic piece, being in the same atmospheric temperature. So that is making the hotness and the coldness. So we should have some specific value. So we can find out here. We can assign a numerical value to temperatures based on our sensation alone. So I have given just now the example. If I touch this one plastic or one wood with one copper, I will feel that the copper is more cool. It means the temperature is much cooler? No. So our sense may not give the correct values. So we need some scales, some instrument by which we can measure the correct value of the hotness and the coldness, and this is called thermometers. So we cannot assign the numerical value to temperature based on our sensation alone. It is not sufficient. Our senses may be misleading. Just now I gave the example. I am sitting in this chair. It is a plastic chair, and if I sit in some metal chair, then I feel that metal chair is much cooler than this plastic chair. So it is because of my sense is feeling that metal is much cooler. This my sense is not correct because it is not much cool, but it is taking more heat from the body. So I feel that it is a cooler, much cooler than the plastic chair. Material properties change with temperature in a repeatable and the predictable way, and this forms the basis for accurate temperature measurement. So material properties change with the temperature in a repeatable and the predictable way. So we have some materials like water, we have some materials like alcohol, ethanol, mercury. These will give a proper rate. If you heat it, it will go a certain amount, the volume of this thing will increase. And if you cool it, again it will come down to its original position. So these properties are used to form the basis for the temperature measurement. So heat is transferred from the body at a higher temperature to the one at a lower temperature until both bodies attain the same temperature. So if two parts are there, if you see here, the hot coffee cools and the cool drinks get heated. So if you keep one hot cup of tea and keep for 10 minutes, after you feel that it is same temperature as in the environment. If you buy one cool drink, a very cool, and you put for some time in atmosphere, you will see that after that both tea and your cold drinks are in the same temperature. Means if anything which is cooler than the environment or the surrounding, the heat will go from surrounding to inside the cool material, and if any system is hotter than the surrounding, the heat will go from hot to the cold. In this way the system will work. So here this you can see here, I have given one. Two bodies reaching a thermal equilibrium after being brought into contact in an isolated enclosure. So this you can see here that iron at a 150 degree centigrade, copper at a 20 degree centigrade, and after some times if you see here, both will be reaching to 60 into 60, 150, iron is 60 and copper is also 60 degree centigrade, and some heat is lost here, but this both will be in the same temperature. So like this we can see here that next is Zeroth law. What is the meaning of Zeroth law and where it is used? I have already discussed in my previous classes. The Zeroth law of thermodynamics states that if two bodies are in thermal equilibrium with a third body, they are also in thermal equilibrium with each other. Okay, so if by replacing the third body with a thermometer, the Zeroth law can be restated as two bodies are in thermal equilibrium if both have the same temperature reading, even if they are not in contact. So I can, so in this way that if two bodies are here, what is the Zeroth law? I will just say here. One body is here, A, another body is C, and these bodies are in contact with a diathermic wall. This is a diathermic wall, means this wall will allow the transfer of heat from here to here. And another system, if I see here, A and here is the B, they are also in the same. So what will happen? AC, AB. So this B and C, this will be also in the thermal equilibrium. So if you take a thermometer and you put here, and if this is giving the 50 degree centigrade and this is giving the 50 degree centigrade, you will tell that this is also in 50 degree centigrade. So this is the basic principle of the thermometer, and this is the thermometer. So like this we can, different scales are here for this thermometric operations. So conversion of temperature scale, one example I am just putting. During a heating process, the temperature of a system rises by 10 degrees centigrade. We are heating the system, like this is the 1x degree centigrade initial, and we give some here heat, and now the temperature is x plus 10 degrees centigrade. Express the rise in temperature in Kelvin, Fahrenheit, and the Rankine. Okay, so here the temperature rise of a system is to be expressed in different units. This is the solution, means Kelvin, Fahrenheit, and the Rankine. So analysis, this problem deals with temperature changes which are identical in Kelvin and the Celsius scales. So change in temperature in Kelvin is equal to change in temperature in degree centigrade. So here this 10 degree centigrade can be made as a 10 Kelvin because it is a difference in temperature. Same way, if we write here the temperature change in Fahrenheit and the Rankine scales are also identical and are related to the changes in Celsius and the Kelvin scale through equation this one. So here delta TR is equal to 1.8 delta T K. So K is equal to 10K. So 1.8 into 10, this will become 18 Rankine. So like this we can, if there is a change in temperature, it is very simple to convert from one scale to another scale, and in this way we can transform the system from one scale to another. So this is the reference, that is Y. Sengel, Michael A. Bowles, Thermodynamics and Engineering Approach, Tata McGraw-Hill's. I have used the resources from this. If any questions, you are welcome to ask to my mail, that is ydwedi@gmail.com. Thank you very much. Also, I request to like and subscribe. In the next class, I am going to discuss in detail about the first law of thermodynamics. This is my for the next class, and so many numericals I will be going to discuss their applications. All of these things will be as per the application point of view. My all lectures will be as per the application in the real industry. That is the objective, and we as engineer, we should be able to apply our knowledge for the real problems, and all the problems will be related to this thermodynamic course will be from the real application on day-to-day basis. Thank you very much for the joining. Be tuned for my next lecture. Till then, goodbye and see you.
Like, share and subscribe. Hit the bell icon for more updates.